Hello everyone, welcome back to Heat Transfer. This is Dr. Tian. This class will move on to Chapter 8, Internal Forced Convection. Similar to Chapter 7, the concept part of Chapter 8 is also short, but application is not that easy. So we'll also be working on a good number of practice questions to understand concepts. So what is internal flow? Internal flow is flow inside a pipe or a duct. We know external flow is bounded only at one surface, and on the other side, it is unbounded. In contrast, internal flow in a pipe or duct is completely bounded by solid surfaces. Similar to external flow, we also confine our attention to internal flow of forced convection. Although the theory of fluid flow is well understood, but we have only obtained theoretical solutions for a few simple cases. So similar to Chapter 7, in Chapter 8, we'll also focus on experimental results and empirical relations for our internal flow analysis. We know in Chapter 7, external flow, we often work with the mean temperature and the free stream temperature. And the reference velocity we often use is the free stream velocity. But in internal flow, we often work with an average velocity instead of the free stream velocity. If we look at the point along the plate, we know temperature is not uniform. Due to the non-slip condition, temperature at the surfaces is 0, and temperature in the center is the largest because it's the least affected by the viscous effect. The average velocity we're talking about here is the average of this. Here, m dot represents mass flow rate. We know it is density multiplied by volumetric flow rate, and volumetric flow rate is velocity multiplied by cross-sectional area. So for an incompressible flow, that is, density is constant. If cross-sectional area is a constant too, then the average velocity would remain constant. We can also express mass flow rate in this integral approach. Let's consider a differential volume at R is R. Then we can calculate the mass through this differential volume by density multiplied by the volumetric flow rate through this differential volume, which is the velocity at this R multiplied by the cross-sectional area of this differential element. From this, we can calculate the average velocity using this integral approach. Here, this dAc is 2 pi r dr. Remember, dAc is the area of this infinitesimal ring. The inner radius is r, the outer radius is r plus dr. And this dAc is pi r plus dr squared minus pi r squared. And this is pi r squared plus dr squared plus 2r dr minus pi r squared. So pi r squared and pi r squared canceled out. And we know dr is infinitesimal, so dr squared would be even smaller. For example, if dr is 0.1, dr squared is 0.01. So we ignore dr squared, and this is 2 pi r dr. Then we take the constant 2 over r squared out of the integral. We have this. Again, in external flow, we worked with the film temperature and the free stream temperature. With internal flow, we often work with an average temperature or a mean temperature. Let's look at this case. Assuming the surface is hotter than the fluid, then those fluid particles adjacent to the surface have higher temperature than those fluid layers in the middle. And the mean temperature we're talking about here is the average of these temperatures. We define mean temperature using this equation. And here, this infinitesimal mass flow rate is density multiplied by volumetric flow rate. By rearranging this equation, we can get the mean temperature in terms of velocity distribution and temperature distribution. Note again, this mean temperature here is the average temperature at a specific X location along the pipe. Similar to chapter 7, one of the most important things for this chapter is to be able to select the appropriate correlation. To choose an appropriate correlation, one of the first things is to determine whether the flow is laminar or turbulent. Note, this is different from external flows. We know for external flow, at first it could be laminar flow, then it could develop to turbulent flow. But for internal flow, it's either laminar flow or turbulent flow. That is, if it's laminar flow, it's always laminar flow. If it's turbulent flow, it's always turbulent flow. Let's look at Reynolds number. We know it's Vd over mu. And in internal flow, we work with this average velocity. Remember, the average velocity for incompressible flow with constant cross-sectional area is a constant. So Reynolds number is a constant along the pipe, which is different from external flow. Remember, with external flow, the Reynolds number is Vx over mu, which increases with x. So external flow could develop from laminar to turbulent. But for internal flow, since Reynolds number is a constant, so it's either laminar or turbulent. We know for external flow over a flat plate, the critical Reynolds number is 500,000. Then what about internal flow? Under most practical conditions, the flow in a pipe is laminar for Reynolds number smaller than 2300. The flow is fully turbulent for Reynolds number larger than 10,000 and transitional in between. But please pay attention here. It should be kept in mind that in many cases, the flow becomes fully turbulent for Reynolds number larger than 4,000. Especially when designing piping networks and determining pumping power, we want to take a more conservative approach. In this course, flows with Reynolds number larger than 4,000 are assumed to be turbulent. Now let's look at Reynolds number again. It is Vd over mu. This mu is the kinematic viscosity, and this kinematic viscosity is dynamic viscosity divided by rho. We can also express this average velocity in terms of mass flow rate. Then Reynolds number in terms of mass flow rate is this. Note here, students are expected to be able to calculate the Reynolds number in terms of average velocity. You're also expected to be able to calculate the Reynolds number in terms of mass flow rate. For flow through non-circular tubes, the Reynolds number and Nusselt number can be calculated based on the hydraulic diameter. Hydraulic diameter is 4 times of the cross-sectional area divided by the perimeter. The hydraulic diameter of a circular tube is d. The hydraulic diameter for some other geometries is listed here. Please review this yourself. Different from external flow, there's another different concept for internal flow, the entrance region. As the flow enters a pipe, velocity boundary layer develops in the pipe, and velocity profile changes along x. Eventually, velocity boundary layers reach the tube center. They merge together, and the velocity profile does not change anymore. The region from the pipe inlet to the point where velocity boundary layers meet in the center is called the hydrodynamic entrance region. Flow in this region is called hydrodynamically developing flow, where the velocity profile changes along the x direction. And the length of this region is called hydrodynamic entry length. The region beyond the entrance region is called hydrodynamically fully developed region. The flow in this region is called hydrodynamically fully developed flow. Similar to velocity boundary layer, thermal boundary layer develops in the pipe when there's heat transfer between the pipe surface and the fluid. As thermal boundary layer developing in the pipe, eventually they merge in the center. And this region is called the thermal entrance region. Beyond this region is called the thermally fully developed region. The length of the thermal entrance region is called thermal entry length. Here I have a question for you. We know in hydrodynamically fully developed region, velocity does not change with x anymore. Is it true that in thermally fully developed region, temperature does not change with x anymore? The answer is no. As long as the temperature of the pipe surface is different from the fluid would keep losing or gaining heat from the surface, then temperature would keep changing. So in thermally fully developed region, temperature would still be changing. But the dimensionless temperature profile remains unchanged. Mathematically, we express it like this. So it is this dimensionless temperature remains unchanged, but temperature is still changing. The region where the flow is both hydrodynamically and thermally developed is called fully developed flow. That is, if a flow is hydrodynamically developed but thermally developing, it is not called fully developed flow. Now the question is, how do we decide whether a flow is hydrodynamically developed or developing? It's thermally developed or developing. Now we present equations to compute entry length. These two equations are for laminar flow. And here H represents hydrodynamic, T represents thermal. Say if you have a pipe, first you calculate Reynolds number. You find it's smaller than 2300. Then you know it's laminar flow. Say the length of the pipe is L. Then we can use this equation to calculate hydrodynamic entry length. Say it's L prime. If L is smaller than L prime, that means your flow is hydrodynamically developing. Your flow has not passed the hydrodynamic entrance region yet. For turbulent flow, we see the formula is simple. Hydrodynamic entry length and thermal entry length for turbulent flow are of the same size. They're both 10 times of the diameter. That means as long as the length of your pipe is 10 times larger than the diameter, then by the end of the pipe, the flow is fully developed already. We also see the hydrodynamic and thermal entry lengths are independent of Prandtl number. You know, Prandtl number is a fluid property. This is because in turbulent flow, the intense mixing during random fluctuations usually overshadows the effects of molecular diffusion. That is, the strong random fluctuations in turbulent flow is dominant. So fluid properties do not have a significant effect on entry length of turbulent flow. Before we look at empirical correlations, now let's work on some general thermal analysis. Let's consider this flow in the pipe. Let's assume the surface is hotter than the fluid. So fluid receives heat from the surface. As the flow enters the pipe, temperature is Ti. As the flow leaves the pipe, temperature is Te. So Te should be larger than Ti. We know given the temperature change of fluid, we can find the corresponding energy change by Cm delta T. Note this temperature difference is between Te and Ti. Both Ti and Te are of the same fluid. Also, at any location x, we can apply Newton's law of cooling. The heat flux is local convection coefficient multiplied by temperature difference. You know this should be the temperature difference between the surface, Ts, and the temperature of the fluid. What is the temperature of the fluid? Yes, remember we use the mean temperature Tm to represent the average temperature at the location x. If the surface is subjected to constant heat flux, then we can express the total heat transfer rate by heat flux multiplied by the surface area. In the meantime, we can also express this heat rate by Cm delta T. From this, we can obtain the exit temperature in terms of inlet temperature Ti and surface heat flux Qs. If we apply Newton's law of cooling for any x, then heat flux is equal to H multiplied by temperature difference between the surface and the fluid. Again, the temperature of the fluid is the mean temperature here. From this, we can express surface temperature Ts in terms of the mean temperature of the fluid and Qs. What about surface temperature remains constant? Let's consider this differential volume. Temperature on the left of the differential volume is Tm. Temperature on the right of the differential control volume is Tm plus dTm. So the temperature change experienced by the differential control volume is dTm. Multiply this by C and M. We find the energy change of this differential control volume. In the meantime, we know this energy change is due to convection into the fluid. We can also use Newton's law of cooling to compute this heat transfer rate, which is H multiplied by temperature difference between the surface and the fluid. It is Ts minus Tm multiplied by dAs. You know this dAs should be the surface area. So dAs is the perimeter multiplied by dx. This P should be the perimeter of the cross-sectional surface. Let's write dTm as negative d Ts minus Tm, since Ts is a constant number. Plug these two equations into this original equation and use separation of variables. We can have this. Let's integrate both sides of the equation. X increases from 0 to x is L. At x is 0, i.e. the inlet, the fluid temperature Tm is Ti. At x is L, the exit, the fluid temperature is Te. From this, we get the natural log of Ts minus Te divided by Ts minus Ti. It is negative HAS mCp. By rearranging this equation a little bit, we get an important equation. This relation gives us the relation among the three temperatures, Ts, Ti, and Te, if Ts is constant. So given surface temperature and inlet temperature, we can find the exit temperature. Or given exit temperature and surface temperature, we can find inlet temperature. Anyway, given any two of the three temperatures, we can find the third one. If we plot this temperature, it looks like this. So fluid temperature Tm approaches the surface temperature exponentially. Laminar flow in tubes. In fluid mechanics, we learned about pressure loss, friction coefficient, head loss, and the required pumping power to overcome the pressure loss. In this course, we'll focus on heat transfer. Now let's start to look at empirical correlations for internal flow. First, let's look at the correlations for fully developed laminar flow. We know if Reynolds number is smaller than 2300, then it's laminar flow. And fully developed flow requires the flow to be both hydrodynamically and thermally fully developed. If it's fully developed laminar flow with constant surface heat flux, then the Nusselt number is simply a constant 4.36 for a circular tube. For fully developed laminar flow with constant surface temperature, the Nusselt number is a constant 3.66 for circular tube. The thermal conductivity K should be evaluated at the bulk mean fluid temperature. What is the bulk mean fluid temperature? Say we have a flow in the pipe. At the entrance, the mean temperature here is Tmi. At the exit, the mean temperature is Tme. The bulk mean temperature is the average of these two mean temperatures. The bulk mean temperature is Tmi plus Tme divided by 2. As for fully developed laminar flow in non-circular tubes, we can find the Nusselt number relations in table 8-1. So once we find the Nusselt number for those non-circular tubes, we can calculate the convection coefficient from this. And this dH here is the hydraulic diameter. Again, this table summarizes the Nusselt number for fully developed laminar flow in tubes of various cross-sections. Remember, we just had several correlations for fully developed laminar flow. How about developing laminar flow? Now we present 3 correlations for developing laminar flow in the entrance region. Please pay attention to the conditions of each correlation. The first correlation is for tubes subjected to constant surface temperature. Remember, from one of the previous slides, we know for fully developed laminar flow with constant surface temperature, the Nusselt number is a constant number, 3.66. Now let's look at this correlation. As L reaches infinity, this is 0. So the Nusselt number is just 3.66, which is consistent with our results from fully developed laminar flow. Please pay attention here. This correlation assumes the flow is hydrodynamically developed. So if you have constant surface temperature, hydrodynamically developed, and thermally developing, then you could use this correlation. But this correlation can also be used for flow developing hydrodynamically when Prandtl number larger than 5. That is, if you have a constant surface temperature, hydrodynamically developing, thermally developing, you may also use this correlation, providing Prandtl number is larger than 5. Remember, Prandtl number is the ratio of momentum diffusion to thermal diffusion. For fluids with larger Prandtl number, thermal diffusion is not as significant as momentum diffusion. So it is closer to the case of hydrodynamically developed but thermally developing. The second correlation here is also for developing laminar flow in the entrance region. You can almost use this correlation for all the cases where the first correlation does not work. For example, if you have a constant heat flux, then you cannot use the first correlation, but you can use the second correlation. Another example, if you have hydrodynamically developing and thermally developing flow, and Prandtl number smaller than 5, then you could not use the first correlation, but you can use this second correlation. The third correlation here is also for developing laminar flow in the entrance region. This correlation is for flow between isothermal parallel plates. Say if you have 2 flat plates and you have a flow in between, then you could use this correlation. So we first had correlations for fully developed laminar flow. Then we had correlations for developing laminar flow. What about turbulent flow? Actually, in heat transfer 1, we'll only cover fully developed turbulent flow. We will not cover developing turbulent flow. Does it make sense? Remember, for turbulent flow, it's easy to reach fully developed flow, as long as the length of the pipe is 10 times larger than the diameter. So in engineering, more often we encounter fully developed turbulent flow, in contrast to developing turbulent flow. The correlation for fully developed turbulent flow has a compact form. It's called the Ditto-Spolter correlation. Note, if the fluid is heated by the surface, N is 0.4. If the fluid is cooled by the surface, the value of N is 0.3. This Ditto-Spolter correlation can also be used for non-circular tubes by replacing the diameter D with the hydraulic diameter. Now let's look at a special case, flow-through tube annulus. The hydraulic diameter, remember, is 4 times of the cross-sectional area divided by perimeter. The cross-sectional area is this. The perimeter is the summation of these two. So the hydraulic diameter for annulus tube is outer diameter minus inner diameter. For this special case, fully developed laminar flow in an annulus with one surface isothermal and the other adiabatic, we have the Nusselt number. Pay attention here. For each case, for each di over to, we have 2 Nusselt numbers. One is for fluid near the inner surface. The other is for fluid over the outer surface. Say we have a fluid in this tube. If you are more concerned about heat transfer between the fluid and the inner surface, you should use this inner Nusselt number. If you're more concerned about heat transfer between the fluid and the outer surface, then you should use this Nusselt number. Note the D here is the hydraulic diameter for both Nusselt I and Nusselt O. Over the semesters, I noticed students often use DI for Nusselt I and DO for Nusselt O, which is not correct. Now let's look at an example. Hot air enters this duct at temperature 103. By the time it leaves, temperature is cooled to 85 degrees Celsius. The ambient air temperature is 0 degrees Celsius. The external convection coefficient is given. First question, calculate the heat loss from the duct over the length. Do you know which equation you should use? I'd recommend that at this point you pause your video and think of this question. I'll give you a hint. Initially, temperature is 103, then temperature changes to 85. So we know the temperature change of the fluid. Then can you find the energy change of the fluid? Yes. Q is Cm delta T. Delta T is TmL minus TmO. This TmL represents the mean temperature at axis L, the exit. TmO represents the temperature at axis 0, the inlet. Since TmL is 85 degrees Celsius, TmO is 103 degrees Celsius, and the mass flow rate M is 0.05 kilograms per second. As for the specific heat, we should evaluate it at the bulk mean temperature, which is the mean temperature of the two mean temperatures. From tables, we can find its value. Then plug in numbers, we can find the heat loss. Temperature decreases, the fluid loses heat, so heat rate is negative. The second question, we want to determine the heat flux and the duct surface temperature at axis L. How do we determine this? Let's check what we have. We have the fluid temperature at the exit, which is 85 degrees Celsius. We have temperature of the outer fluid, which is 0 degrees Celsius. We want to find the heat flux at the exit, and we want to find the surface temperature at the exit. Again, I recommend that you pause your video here and try to work this out yourself. Let's draw the thermal circuit. So we have the fluid temperature, TmL. Between the fluid temperature and the inner surface, there is a convection resistance. Then we reach temperature Ts. Between Ts and T infinity, we have another convection resistance, which is T infinity. What about the conduction resistance within the wall? Note the question did not suggest the thickness of the wall. Also, it mentions it's a sheet metal. This implies the thickness of the wall is thin. So we neglect the conduction resistance within the wall. Between fluid inside and fluid outside, we have two convection resistances. And these two resistances are in series. We have this heat flux going through. And this inner convection resistance is 1 over H. Let's use Hx at axis L to represent it. This outer resistance is 1 over HO. If the inner convection coefficient was provided, this problem would be very much similar to one of those in chapter 3. So now we need to find this Hx. We had several correlations in chapter 8. Which one should we use here? Remember, we need to check its laminar flow or turbulent flow. We also need to check it's in entrance region or fully developed region. First, let's calculate Reynolds number to determine its laminar or turbulent flow. Mass flow rate is provided in this question. So let's express Reynolds number in terms of mass flow rate. Mass flow rate is 0.05. Diameter is 0.15 meters. The mu, this viscosity, we should use the viscosity at which temperature? Should we evaluate this viscosity at the bulk mean temperature? Not really, since we're concerned about heat transfer at this local point. So we need the viscosity at this local temperature, 85 degrees Celsius. This is larger than 2,300. So we conclude the flow is turbulent. Now we know the flow is turbulent. Next, we should check whether the flow is fully developed or still in the entrance region at axis L. How do we check this? Remember, we have formulas for calculating entry length. For turbulent flow, the hydrodynamic entry length and thermal entry length are of the same size. They are 10 times of the diameter. So we just need to check the ratio of the length of the pipe divided by the diameter of the pipe, which is 50 over 0.15. It is 33.3. This is larger than 10. This means the length of the pipe is larger than 10 times of the diameter. This means at the end of the pipe, the flow is fully developed already. So now we conclude we have fully developed turbulent flow. Which correlation can we use? Actually, we only have one correlation for turbulent flow, which is the Dietz-Boelter correlation, which is valid for fully developed turbulent flow. Let's plug in numbers. Reynolds number, we have already calculated. Prandtl number, we can find it from tables. Then we can calculate the convection coefficient at axis L. This thermal conductivity we can find from tables. So this is 11.5. Now we can calculate the heat flux. Remember, we have two resistors. This is TML, this is T infinity. This is TSL. So heat flux is 85 minus 0 degrees Celsius divided by 1 over inner convection coefficient, which is 11.5, plus 1 over outer convection coefficient, which is 6. This is 335 watts per meter squared. Now we can also calculate this temperature. Since Q dot is TML minus TSL divided by 1 over convection coefficient at axis L. From here, we can get TSL. Plug in numbers.